Okay, so as I was saying, inside the stars, this is oval shaped. Anyway, this is an approximation. Now we can have atoms and photons, but you see the pressure and temperature are very high, as a result of which most of the time atoms, they becomes either free of electrons and plus ions, right? They disintegrate in this way, and so as a result we have electron, ion and photons, right? Now, so what is the gas pressure? The gas pressure, if you consider only atom, then the gas pressure for the atom will be pressure due to electron plus pressure due to ion. Now, how to talk about this pressure due to ion? We have introduced the concept of mean molecular weight. Same here, we have also used mean molecular weight for electron. These concepts we have introduced. What about photons? And then the expression for pressure, that is basically the EOS. So EOS basically the pressure expression. This is it, right? Now for photons, remember in the last class we derived the expression for radiation pressure, and that is basically the equation of state for photons. Okay, so far so good. So what do we do today? Now you see there will be complications because these things we have to keep in mind that the temperature and the density, they change inside the star as we go into the deeper areas, deeper parts. And sometimes because of these changes, the equation of state changes drastically. Today we'll be talking about the case for electrons. And so basically today I'd like to talk about degenerate gases. When an electron becomes degenerate electron? So basically our topic is degenerate gases. It's a very general topic. Now before I start, let me first talk about, so basically you have to understand that when I'm talking about degenerate gases, basically I'm talking about the quantum behavior of the gases. Till now I have been treating them as classical particles, distinguishable. Now what I am saying is that as we go for higher density regions, there is a possibility that, not just possibilities, it is reality, that the ions will come closer to each other, electrons will come closer to each other, and then what will happen? You will see that the interatomic distance might become of the same order or even lower than that of the de Broglie wavelength. Then under those scenarios, what happens is that the quantum behavior becomes important, right? Now to discuss what quantum effects become important, let us first talk about the distribution functions. Okay, now you see the distribution function of the particles in a gas according to their energy depends on the appropriate statistics, right? Now in the classical limit, for identical and distinguishable particles, we have the Maxwell-Boltzmann distribution, right? And what is this distribution? Well, basically we have this, you see here, where I have written down the density Ne of particles with energy E, right? So density of particles with energy E, right? Note that here this Ge is basically the statistical weight of level E. That is basically the number of possible configurations per cubic centimeter with energy E, or number of possible config per centimeter cube with energy E. Right. Now also there is something very important, alpha. What is this alpha? Alpha, this parameter, is known as the degeneracy factor, and this depends on the particle density, which can be determined from the density normalization condition. Now it is important to note that for very low density, let me write down here, so we are talking about alpha. Now low density, for this case we have alpha is much greater than 0. For very high density we have alpha is less than 0. Remember that for photons the value of alpha is basically 0. Okay. Now, so we have talked about classical particles, the distribution. What about quantum particles, which are identical and indistinguishable? Let us talk about identical and indistinguishable particles with half integral spins. So basically fermions. Now examples of fermions: electron, proton, neutron, neutrino, right? And for them we have the Fermi-Dirac statistics. Let me write it down in a very short form here. Okay, so this is the Fermi-Dirac statistics. Finally, let us talk about bosons. Right, so we are talking about again identical and indistinguishable particles, but this time with integral spins. And what are the examples? Say for example here we have examples as electron, proton, neutron, neutrino. This time we have examples like photons, helium nuclei, then pi mesons, right, just to name a few. And let me write down the Bose-Einstein statistics, yes, here. So number of particles here. Okay, so this is the particle density according to the Bose-Einstein statistics. Now apart from the particle density, the occupation number or occupation index alpha, right, no, not alpha, occupation index is also sometimes used. So occupation factor. Now this is given by Fe equal to N of E divided by Ge. So this is basically the occupation probability of a state with energy E. Right. Now in the case of Maxwell-Boltzmann distribution, note that we have f of E is equal to exponential minus alpha plus E by kT, K being the Boltzmann constant. Right. And for alpha much greater than 0, we have f of E less than, much less than 1. Now you see, to study the physical conditions in the stellar interior, we will consider not Maxwell-Boltzmann, we have already did some study previously. We will consider the pressure term due to electrons, which follow the Fermi-Dirac statistics. Okay. Now, for Fermi-Dirac statistics of fermions, you see, the occupation factor is given by this term. Now, it is important to note that for, as I have already told you before, for high density alpha is less than 0. Okay. Now for fermions, in the case of fermions, then we obtain the limit f is less than equal to 1, which is implicitly established by Paulis principle. Right. By Pauli principle. Say for E by kT is equal to alpha, what do we have? We get F is equal to half. Right. If the temperature and density are such that, alpha is much greater than 0, that means low density, then you will immediately see that what will happen? Tell me. Let me give a numbering of equations. This is, say, equation number 4. Okay, in this way I will be able to match with the previous lectures as well. This is Maxwell-Boltzmann number of particle expression, right? Equation number 4. Then for fermions, this one, this is equation number 5. This is equation number 6, Bose-Einstein, right? And finally, this one, which we have, yes, discussed just now, this is equation number 7. So, you see, what I was saying is that if temperature and density are such that alpha is much greater than 0, that means low density, then what happens is that equation 5 gets reduced to equation 4. Okay, so let me again take a look. What is this? What I am talking about? Of course, I am talking about FD statistics becoming equal to the Maxwell-Boltzmann statistics, right? This is what I was telling previously. So, in this case, we have the FD distribution. It tends to become Maxwell-Boltzmann distribution. Okay. Okay. So now let us, with this introduction, let us now discuss degeneracy. Now you see the density of states, no, not the density of states right now. Let me talk about density of particles first. You see, the density of particles with energy E, what is its relation with occupation index? Well, basically it is given by, you see, Ne equal to Ge into Fe. Now for continuous distribution of energy states, we can define the density of states as GEDE, which is basically the number of states per unit volume with energy between E and E plus dE. Okay. Now, in the momentum space, we can analogously define momentum space. We can analogously define Gp, dpx, dpy and dpz as the number of states, again per unit volume, such that px component of vector p momentum is the interval px to px plus dpx and so on. On the other hand, what does Heisenberg's uncertainty principle tell us? Well, uncertainty principle, from there we have delta x, delta px is of the order of delta y, delta py is of the order of delta z, delta pz is of the order of h. Now, the uncertainty in position associated with, so you see the uncertainty in position associated with particles with momentum p is then delta x of the order of h by dpx. Right? Now, similarly, delta y h by dpy and delta z h by dpz, so that the uncertainty in volume, how much is it? It is basically delta x, delta y, delta z, and that is of the order of h cube divided by, you see, dpx, dpy, dpz. Right. Now, in order that the states can be resolved and identified, okay, so you see, in order to resolve and identify the states, each volume, delta x, delta y and delta z must be associated with a given state. This is important, right? Therefore, the number of states per unit volume is basically inverse of uncertainty volume. So namely, what I am telling is that Gp, dpx, dpy, dpz is of the order of 1 by h cube dpx, dpy, dpz. Now, in thermodynamic equilibrium, the particle momentum is isotropic, right? In thermodynamic equilibrium, particle momentum, there is no fixed preferential direction. In equilibrium, particle momentum is isotropic. And so, we will be interested in the density of states. So, we will be interested in density of states having this value between P and P plus dP. Now, in this case, you see, we can write here. So, I am writing in terms of momentum space, right? It is important to note that there is a factor 2, and this factor, this 2 factor, this takes into account the splitting of states due to 2 degrees of freedom of polarization for electrons and photons, so that this above relation is valid. It is valid for both of them. Okay. Now, in terms of, so let me do the numbering keeping in mind previous lectures, which basically fill the gaps in between regarding the mean molecular weight and radiation pressure concept. So this is equation number 22. Okay. Now, using this equation and this fact, we then have, you see, let me write down. Okay. So we have then this relationship. Note that since the occupation factor F is less than equal to 1, now this is equation 23, so the density NP we have this relationship. This is very interesting here. Now this relation has great consequences. What happens is that, you see, as the gas density increases, the electrons are forced to occupy states with higher momentum, since the states of lower values of momenta are already occupied. Remember, this is what fermions are. We are talking about fermions, right? So, and we know that as the density increases, the electrons are forced to occupy states with higher momentum, since the states with lower momentum are already occupied, according to this limit over here. Now, in this case, the electrons with larger momentum values will have an important contribution to the gas pressure, and this is known as degeneracy pressure. So, basically, the electrons with larger momentum values, they contribute to gas pressure, and this is basically known as degeneracy pressure. Now this phenomena can be very nicely, you see, we can show this by considering a section of the 6-dimensional phase space. Let me show you here in this diagram. So basically I have shown you a section of 6-dimensional phase space, right? Now what is important is what we are showing you is basically the momentum distribution, how it changes with increasing density, and this is the case A, B, C, D, E, F. Okay, now you see for lower densities the momentum distribution, this one NPX, around the x-axis it follows the Maxwell-Boltzmann distribution here A. So this is A corresponds to, just a second, yes, so this A corresponds to MB distribution, low density, right? Now as the density increases, what happens? You see, say for example, let us double the number of electrons in the same volume while keeping the same temperature. Then this distribution is this B. So B is basically, density is twice density of case A but same temperature. Now see what is happening. You see what, there is a slight change, but still it is Maxwellian. Now if the density is further increased, this behavior will not repeat. Why? Now you see what behavior I am talking about. Previously I told you that I have just doubled the density keeping the same temperature. Now you see the same thing over here can be seen, where each value of the ordinate is twice as large as the curve A for B. But if the density is further increased over here, here and so on, this is higher densities. So this case belongs to higher density. Increasing density. Okay, now as I was saying, if we increase the density further beyond B, the behavior will not repeat. Now why is this happening? This is because of, you must remember, this is happening because of this restriction given by the Paulis principle. And what is this? This is basically the restriction due to Paulis principle, Paulis exclusion principle. Okay, now so what happens is that the gas density in the phase space is bounded, as we have seen from this relationship over here. Therefore, as the maximum value of the distribution function approaches the upper limit, what happens is that the cells in the phase space with lower momentum will be already full, so that the additional electrons must occupy cells having higher momentum or higher energy. And now this results, what does it result? This results in a deformation. You see this area from here to here, the behavior, whatever it is, from here to here, it is very different. So there is a sort of deformation. Right. So we have a deformation of the distribution function, and as a result of this deformation, the distribution function, it does not resemble the Maxwell-Boltzmann distribution. This is still a Maxwellian distribution, but these are this E, D, E, F. They don't resemble Maxwell distribution at all, and is also not a function of temperature. Now this can be easily, you can see here in these curves D, C, D and E, where increasing the degeneracy degrees we have considered. Now in the final stage where the degeneracy is complete, so this is the case, complete degeneracy. What happens here? In this case, you see all momenta cells below a certain limit PF are occupied here. This is PF, right? This corresponds to PF. They are filled. While the cells with momentum larger than PF are empty. Now let me again show you the difference between degenerate and non-degenerate gas in this momentum distribution plot at different temperatures. Okay, now you see this is the restriction given by the Paulis exclusion principle. So this is the restriction. So this is due to Pauli, which means that all the fermionic states, they must be on this side, not on this side. Right. Now, say for example, here you see we have shown you the distribution for T is equal to 10 to the power 6 Kelvin and then T is equal to 10 to the power 7 Kelvin. And the density in this case for both of them, the density is N is equal to 10 to the power 26 per centimeter cube. Now, what is important to see that apart from this relationship, I am shown you this thing so that you can calculate this using Maxwell-Boltzmann distribution and see that indeed it is so. Now, if the Maxwell-Boltzmann distribution is valid, what happens is that decreasing the temperature from here to here, if we decrease the temperature at constant density, then what happens? This basically corresponds to distribution of peak at lower momentum, right? Why? This is because Pmax according to Maxwell-Boltzmann distribution is basically twice Me Kb T to the power half. So lower temperature means lower Pmax. You see this thing, this peak, it has shifted to lower value. Now we see that for a given electron density, the MB distribution is no longer valid for sufficiently low temperatures. The same naturally occurs for a given temperature if the particle density is sufficiently high. Now tell me, if this is not valid, then what will be valid distribution? Tell me. Can anyone tell me? I am telling you that this distribution which we have shown here, this is not valid. So what will be the distribution at T is equal to 6, 10 to the power 6 Kelvin? At higher temperature here, you see this is the distribution plot. Now interestingly, this distribution plot corresponds to the Maxwell distribution, and you see this is okay, perfectly okay, considering the restriction of Paulis principle. But if we decrease the temperature, the MB distribution predicts this part, whereas since these are fermions, and decreasing the temperature means effectively the particles are now coming closer to each other, right? So the quantum behavior will be manifesting, and as a result this distribution is not valid. So I am asking you, what will be the new distribution? Can anyone give me some light on this matter? You see, what will happen is that since everything must follow this line, so this new distribution will be like this. You see here. Something like this. So instead of this distribution, we will have this distribution. So what is happening previously, if the MB distribution was correct, then we will be having this distribution, right? But this is not so, since all particles must fall on this side of the plot restriction. So we have a new distribution, and the area is the same since the number of particles is the same. But note the difference. Main difference is this. See clearly. If this has been the case, then the average momentum value will be here. Whereas if the new momentum distribution is this, then the average momentum is somewhere here, which is higher. So this is higher momentum. So this is the origin of degeneracy pressure. That means instead of this plot, we have now this plot. So here we have classical concept, and here we have degenerate matter concept. Understand? Now what will happen if we decrease the temperature even more? What will happen? You see, if we decrease the temperature even more, then the classical prediction will tell us something like this, right? But again, this is not valid. Suppose this is the temperature corresponding to 10 to the power 5 Kelvin, right? But this again will not be valid, and the new distribution will be again like this. Understand? Same thing on this part. So the new distribution also will be somewhere on this part as well. So this is how the distribution of electrons change when we go from classical to quantum regime. And this is all because of this Paulis exclusion principle. Any questions? বলো, জিজ্ঞেস করতে পারো।
অসুবিধা হচ্ছে
কোন জায়গা বলো?
স্যার ওই টেম্পারেচারের ওই মানে যখন কমছে তখন ওই জায়গাটা মানে নিউ ডিস্ট্রিবিউশনটা কেন আসছে ওইটা স্যার একবার বলবেন?
ইয়েস, দাঁড়া আরেকবার বলি। তবে এই ছবিটা তাহলে একটু বড় করে বানাই আবার করে। দেখো বেসিক্যালি যেটা হচ্ছে আমরা জানি, we know if this is Maxwell distribution, as the temperature decreases, what will happen? The peaks, they will become like this, right? This is decreasing temperature, right? But now I am telling you that decreasing the temperature means what? কি হবে? Particles will come closer to each other. You can think of it like that. The thermal motion will be decreasing. The thermal energy decreases as we decrease the temperature. So the particles come closer to each other. When the particles come very close to each other, basically their density will increase. Now the interatomic or inter-particle distance might become quite close to that of the de Broglie wavelength. And as a result, what will happen? The quantum behavior starts manifesting. Now we are talking about fermions, and we know fermions follow Paulis exclusion principle. And what does Paulis exclusion principle say? No two fermions can have the same quantum numbers in a given quantum state. This thing, if I do a plot here, then we have this sort of restriction given by the Paulis principle. As a result, jeta hocche right now, what is happening is that this distribution is okay, higher temperature. This distribution is not okay because this part of the distribution, this is invalid. So what will happen is that this part of the distribution, this will be shifted somewhere over here. So the new distribution will be like this. এই যে দেখো এই রকম করে হলো, হয়ে তারপর এইটা কমে again it will follow this part. So what is happening? These electrons which were not allowed by the Paulis principle, they will be now accommodated in this part of the graph. So there is a shifting. So this is what I am saying. এই যে শিফটিং এর জন্য কি হচ্ছে, ইনিশিয়ালি যদি এই রকম ডিস্ট্রিবিউশন হতো তাহলে অ্যাভারেজ মোমেন্টাম কোথায় হচ্ছে? এইখানে। সো অ্যাভারেজ মোমেন্টাম, বাট ইফ দ্য ডিস্ট্রিবিউশন বিকামস লাইক দিস, অ্যাভারেজ মোমেন্টাম ইজ সামওয়্যার হিয়ার. সো ইউ সি higher value of momentum, right? So this means higher pressure exert. This means that degenerate gas, they exert a higher pressure. Again, independence of temperature. সেটা কি করে হচ্ছে দেখো. You see, if we decrease the temperature even more, তার জন্য কিছুই হচ্ছে না. এইখানে যেরকম ম্যাক্সওয়েল ডিস্ট্রিবিউশনে তুমি পিক শিফটিং দেখছিলে, এখানে কোনো পিক শিফট হবে না. যেটা হবে সেটা হচ্ছে এই যে স্লোপটা আছে, এই স্লোপটা আস্তে আস্তে যত টেম্পারেচার বাড়বে স্লোপটা শেষ হয়ে যাবে. ফাইনালি দিস উইল জাস্ট বিকাম ফ্ল্যাট লাইক দিস at T is equal to 0 Kelvin. And at finite temperature, so at T is equal to 0 Kelvin, it is like this, entirely flat. But at finite temperature, there will be sort of this like of thing, right? So this is finite temperature, and this flat is for T is equal to 0 Kelvin. So basically you can say there is hardly any difference. So this means that this region, this shaded region, is due to thermal electrons, right? Finite temperature electrons or thermal electrons. But again, in the entire distribution, the effect of temperature is quite negligible. It just changes the peak shape very slightly. So in a way, you can say that the equation of state P is quite independent of the temperature, as we will see from the numerical form as well. Okay? বোঝা গেছে? Good. Okay, now this is a very tricky play. I know. Okay. So equation 14, then 15, page number 16. Okay. Now in the conditions of the stellar interior, you see, degeneracy is restricted to electrons, so that ions, you see, ions, they are still non-degenerate even if electrons are degenerate. Now let us consider that the average kinetic energy, so let us consider that the average kinetic energy of ions and electrons are same. What does this mean? That means me V square is approximately equal to mi Vi square. এখান থেকে কি পাবো আমরা? We will find Vi divided by VE is of the order of me by mi to the power half. And as a result, we will have, you see, this relationship. Let me name it equation 25. Okay. Now, for a given volume, ions occupy a volume of the phase space by a factor of how much? You see, for a given volume, ions occupy a volume in phase space by a factor pq proportional to mi by me to the power 3 by 2 larger than electrons. So for example, for protons, we have mp by me to the power 3 by 2 is of the order of 8 into 10 to the power 4. What does this mean? So this means that, what does this mean? So this means that we have considered proton only. This means that the number of cells in phase space available to protons is much larger. How much larger? By a factor of 8 into 10 to the power 4 compared to electrons. Okay? Fine. Okay.